Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Daniel, who has completed one of the courses we offer, our ROS 2 Basics in C++. And at the end of this course, you can present, which is what's happening here, a project based on what you've learned throughout the course. And he's going to be showing us this project, which he did on a real robot here at The Construct. So without further ado, hello, Daniel, how are you?
Hi, Rodrigo. I'm good.
I'm glad to hear that. And yes, whenever you want, you can start sharing your screen and telling us what you've done with your project.
Okay, sure. So I'm going to share. Okay. Can you see my screen?
Yes, I can see the robot and some terminals open.
Okay. Yes, I'm already connected to the real robot. I already launched the ROS2 to ROS1 bridge in order to my programs to communicate with the robot. And yes, we can launch the main launch file that does all the logic and everything, and hopefully the robot must complete a full lap.
Great.
So let me source the workspace and launch okay, so this launches everything. Later I will explain one by one all the nodes what each one of them does.
All right.
But now it exposes an action server. So let me see. The action server should be here. Okay, so we have this ODOM record. So let's call this action server. Start goal.
It's a send goal.
Send goal. I always try to call this send goal. Send goal, and the name is ODOM. We can give it a -F to read the feedback, and the message is in a different package with all the interfaces. And this is the ODOM record interface, and it's an empty message. I have to send it. Okay, so now hopefully, yeah, the robot is doing something.
Yes, we can see that.
And we have some feedback here, and also hopefully some feedback here that is a distance travel. Now it calls the wall finder server. So it's trying to find the wall and align to the wall. And now it's moving, trying to follow the wall, and here is the distance travel. And also if I open another terminal with Airbus, I also have here a configuration file for Airbus. Here is changing from one wall to the other.
I see. Sometimes Álvarez, the first time you run it, it takes a while.
Yeah.
Oh, nice.
Yes, so here we have, I also made these points as reference that where the wall is and where the closest obstacle in front of us is as well.
Wait, I'm sorry. You said that blue thing is where the wall is, and then the red one?
No, the front, the blue is the front obstacle, and this pink is the wall at your right.
Really nice.
At your right, and it already completed a full lap. So here we should have the goal finish, success, and the list of odoms that it was one of the requirements of the assignment that have all the list of the list of all the points.
All right. Awesome. Well, very clear and very nicely executed. Do you mind explaining us just a little bit of how you solved each part?
Yes, sure. So I have here some slides. So can you see the slides?
Yes, we can see the slides now.
Okay. So the main struggle that I had at the beginning is that the laser scan format in the simulation LiDAR is not the same as in the real robot LiDAR. So I could only debug in the real robot for 25 minutes each time. So it was a little bit of a struggle. But the thing is, for this assignment, we need to know the obstacle in front of us and the distance to the wall at our right. So here in the simulated LiDAR, we have the full circle, but we have 360 samples, and it goes from 0 to 2 pi. And in the real LiDAR, we have double the number of samples, and it goes from minus pi to pi. So what I did is this function to give me the index in the range array of the angle that I wanted, independently of the kind of LiDAR.
Right. So whether it's 360 or 1,000, you have this function to avoid that.
Exactly. And also, for instance, the simulated LiDAR, this is the index 0, so it starts from 0.
Yeah, not always though. It depends on. Yeah.
Well, in this particular case, I know. But also in this particular case, in the real robot, it starts here at the index 0 is minus pi, so it's in the back, and it goes all the way to here. So with this function, now it's standardized. Exactly. And also to follow the wall, I find that the most convenient, and maybe not the best, but quite convenient way to do it is to find how parallel is the wall to the robot. So what I do is to look at these two rays, 240 and 300 degrees, and see if both are equal length, means that we are perfectly parallel to the wall. If one is bigger than the other, it means that we are either going towards the wall or away from the wall, so we can adjust. To do this, I also made as well. I also find that in the simulated robot, the LiDAR is quite reliable but very noisy. So instead of just one ray, I took 5 rays and do the average, and also made a moving average from that to reduce the high frequency noise from the lights. And that's the reason I put these points here, so you can see that. Well, here is the real robot. It flickers less, but in the real robot it flickers a lot. But this point is quite stable. I can move it manually. See, this point is quite stable.
And that's because of your filtering, let's say.
Yes, because of the exactly.
Nice.
And here I also have a service. I have a node that is a service called distances. No, sorry, it's a topic. Yeah, it is a topic. It's a topic. Should be distances, and if we here, here type. It publishes this the front obstacle, the distance to the wall, and this parallelism with the wall. And this information
so if it's
also
one, you're parallel.
Exactly. If it's one, you're perfectly parallel. If it's positive or negative, they're working towards the wall or away from the wall.
Mm-hmm.
So yes, at the beginning I start for part 1, so I made everything in part 1. Then I start looking the requirements for part 2, and in part 2 you asked your proposed method was to see all the rays from the laser scan, see the closest one. The closest one is supposed to be the where the wall is.
Mm-hmm.
So you align to the wall and do that. So what I also did.
It's a simplified version of where's the wall because it could be an obstacle. Yes.
Yeah. So I did that note with later I can walk you through the code, but mainly it's a finite state machine. So if you call this node, it finds the wall, meaning that it sees where the shortest ray is and move align to that. What I also did is like a basic proportional control to adjust the speed to the error, how the difference is your angle from where the wall is. Once you are aiming at the wall, you change to approaching the wall. So you move either front or back to adjust the distance to 30 centimeters. And then when you are at 70 centimeters to the wall, you rotate and see when the ray at your right is the closest one, meaning that you are parallel to the wall.
Right.
And then this service finish. And what the main node does is it starts idle at the beginning, and when you call this actions on service, the state goes to wall lost. So it calls the other service to find and align to the wall. The state's here. When the other service returns successful, then you go to the state follow the wall, and it's following the wall until either you lost the wall, then you go back to this state, or you encounter an obstacle in the front, so you move here to transition to the next wall. And what it does is rotates a little bit and then tries to go parallel to the next wall. And it repeats over and over until the lap is complete. And for the lap, yeah.
So what you're doing then is basically in each side of the rectangle, you're finding the wall. So every time when you're done following the wall, then you set that wall lost to true again, I guess, and then you do that again?
Okay, no, exactly. When you're following the wall, it's also, what it does is, if it's completely parallel to the wall, to keep forward. If it's a little disaligned, so keep moving forward, but with a little bit of angular velocity to adjust. If it's the disalignment is higher, that move in place to align to the wall. And if the disalignment is very high and also you are very far or very close to the wall, then it goes to this stage.
I see. Okay, nice.
And if you're following the wall correctly, but you encounter an obstacle in the front at less than, I think it's 20 centimeters, that it goes to this state.
Okay.
Something like that. And yes, for the lab completion, what I did is, well, I don't take into account the first alignment to the wall. Once it's completely aligned, I store this point as a starting point.
From what, like the odometry, or I'm sorry?
Yes, okay. the odometry. Yeah, I'm subscribed to the odometry topic, and I store those values. So once the robot leaves this outer circle, meaning that the Euclidean distance between the center of the robot and this point is bigger than this radius, I set a flag to true, meaning that we leave the goal room
position.
or spot.
Yeah.
Then when it completes the lap, when the distance between the center of the robot and the center of this inner circle is less than this radius, it means that the goal is completed. You did the full lap.
Okay.
This is the logic behind it. And I think that's basically it.
That's it. All right. Let me just fix the screen here since we changed screens. All right. Do you mind stopping sharing your screen so we can go to the questions part of the project? Well, that's a really nice project. All right, here we go. Congratulations, Daniel. Really, really nice project. It's there's a couple of things I really liked that I haven't seen that I want to mention. First of all, I think it's really clever to start the whole process with the action. So that's actually better than how we specify it in the project. So I'm thinking about maybe changing that because it makes more sense that you launch all the nodes and then you have an action that you can call that does everything else. I thought that was really nice. I also really, really liked the spots in RViz. In general, how you're using RViz.
RViz is very useful for debugging. I find it very useful.
Yes, and we want to encourage students, especially people that are getting started with it, that they see it as a kind of that I have to do RViz on top of it. Well, no, it's to help you. And I just wanted to ask you how you did those points, how you made those, because I thought that was amazing, because you can kind of see what the robot, what's happening, and based on what decisions are going to be taking. So could you tell us how you did that real quick?
Yeah, sure. There's a message type that is point 32, if I remember correctly.
Yeah.
So it's just X, Y, and Z. And also RViz has a plugin to represent these points. You can choose the color, the radius, the alpha, and all that stuff.
Right.
So it's quite simple.
Okay, so you extract that those values you were getting, and then you publish them as a point, right? And then that way you can add it by topic on RViz and use that. That's great.
It, yes.
Also, the first time I see it, and I think it's awesome. I also really like the standardizing function that you did for the real versus simulation scenario. I think you're gonna people run into these issues, and I think that's a really nice way to do it. So you don't care about how long your scan is, and I have a lot of things that I like, so I'm just gonna keep going. Also, really liked the way of you doing the wall following, which is based on how parallel you are to the wall, and that the fact that you also added that extra debugging topic, the distances, is really nice. I was wondering if you thought it was a service as opposed to a topic, and
I did a lot of refactor through the process.
And we can
at the beginning I did everything in the same node, and then I split it into 2 nodes, and I changed a lot of things in the process.
So I was gonna say that's awesome, and we can have a debate whether we leaving it as a topic or maybe putting it as a service since you're doing it to debug. I just really like that seeing this, because it means that you're using all of the tools for ROS 2 that you have learned. And then basically the only question really I had was that so you said you have a state machine for the, is that for the whole process or just because I saw that you had the wall following service part logic and then the wall finder? Is it two separate things, or is it like one combined?
Yes, it's two separate things like that are like kind of nested. One is nested inside the other.
Okay, well, I think that's really great too, and because the fact that you implemented the state machine can make the thing try again, go back, and solve this. And I think you went really above and beyond the requirements. But this gives a lot of people a lot of ideas too on how you can simply take a little while in developing this state machine that will save you so much time, and at the end it will help have a better behavior. So I wanted to say that also was really, really nice. And just one last question that I wrote down. You said you had a speed controller that slowed down. Was that in the wall finder or in the wall follower or in both?
Everywhere. I wanted to implement a PID control, but I didn't want to spend too much time, and I want to keep following courses, so I will have the chance to experiment about that. So I made just a basic proportional control. Yes, both for the angular speed and from the linear speed.
Okay. Yeah, because seeing that parallelism condition you had, I'm sure like you can find like a template class for a PID, and you can use those, right? You can use, because I was like, oh, maybe you can put like that the distances are the same, the two rays that you had, and that way you just run the controller and it automatically will stay. So that's what I'm saying about doing things to help you debug or things like that, because it will give you these ideas that to move forward into more complicated things. But other than that, a really, really nice project, Daniel. Thank you so much for showing us. And
thank you. I had a lot of fun making this project and playing with both the real robot and the simulation.
Great. I'm glad you liked it. It was really, really nice. And to everyone else that is watching, this is what you can do for some of our courses once you're done. To obtain a certificate is to present what you've learned in order for us to really know, and the audience, that you have taken some learnings from our course. So I invite everyone that's watching to do what Daniel here did. And Daniel, thank you again so much, and we'll see you again next time.
Thank you.
All right, guys. We'll see you guys for our next video, which is later today. All right, guys. Bye-bye. Ok, perfecto. Ya está. Oye, muy bien, muy